In this section, I'll leave you to read the outline of the milestones in the development of modern atomic theory and summarize the results of some experiments that led to these theories. And then we will discuss how these theories help describe the three subatomic particles that compose atoms and define isotopes and give an example for several elements. So if you read the history of this, we talk about the nuclear model of an atom. The atom's positive charges were proposed by Rutherford to be concentrated in the nucleus, and these positively charges he called protons. However, the number of protons only accounted for half or less of the atomic mass, and it wasn't until 1932 that Chadwick found evidence of neutrons. These were uncharged subatomic particles with a mass approximately the same as that of protons. So the protons and the neutrons were in this dense nucleus, and the outer cloud was where the electrons lived. So you can look at an atom as being composed of three parts: protons and neutrons, which were about the same size, and electrons, which were much smaller. You needed all three of these parts together to have a functioning atom. And you look at the table below, summarizes the different charges. So the electron is -1, the proton is +1, the neutron is 0. The proton and neutron have a similar mass, and the electron is much smaller, and the proton and neutron are on the inside of the nucleus, and the electron is on the outside. So in the next section, we're going to see how we can write these, and what is the symbolism that helps us explain all these different properties of each atom for each element. And then we're going to look at the atomic mass unit and the average atomic mass units and see how that applies to isotopes and isotopic abundance. So when you look on the periodic table, the first thing you see is a letter. That letter is the chemical symbol for that element, and you can see that here is given by the X. So in the case of carbon, that will be C. In case of other elements, it will be whatever the letter is for that element. In the lower left-hand corner, there is a number, and we refer to that number as Z, and it refers to the atomic number or the number of protons in that element. In the upper left-hand corner is A. That is the mass number, and that is the number of protons plus the number of neutrons. And let's look at carbon again. So the symbol is carbon. It's in the center. Carbon always has 6 protons, and that's why it's atomic number 6. So it also has 6 electrons because the number of electrons and protons are the same. And then the number of protons and neutrons add up to the mass number, which is 12. And you can look at these for any atom on the periodic table. So you can look at the numbers, and from these numbers determine what you need to know. So if you need to determine the number of protons, neutrons, or electrons in each of the following species, the first thing you do is figure out what the atomic number is. Then you can figure out the number of neutrons, and then you can figure out the number of electrons, and then whatever else is left, protons. You can work with any combination of those to figure out what you need to. And recall that for number D here, it says carbon 14, and that means 14 is the mass number. So what we're going to go now is go do some problems directly. So in this case, let me get a pen. Get a little pen, and I'm going to pick a color. So we'll pick purple, and we're going to do chlorine 3517. So the number in the lower left-hand corner, we said meant the number of protons. So the number of protons is equal to 17. The number of electrons is equal to 17 as well. And then the number of neutrons is equal to 35 minus 17. I'll just leave that like that. Now, in the next case, you have an isotope of chlorine, because this one also has 17 protons, because it always does, or else it's not chlorine. So the number of protons are the same. The number of electrons are the same, but now you have more neutrons. So the number of neutrons is equal to 37 minus 17. So in this case, the number of neutrons is equal to 20. So you have more neutrons in this version of chlorine. And for potassium, this is here, we were just given K, so K is potassium. So you go and look on your periodic table. I'm going to pull up my periodic table. Yeah, just a second. And potassium is number 19, so that means the number of protons is 19. And the number of neutrons is equal to 41 minus 19, so that's 21, and the number of electrons is also equal to 19. And then remember we said carbon 14 meant that that was the same as writing 14 up here, and carbon on your periodic table is always 6, because 6 is carbon, so it has protons that are equal to 6. The neutrons now are equal to 14 minus 6, which is 8. And then again, so this is an N. And the electrons are always the same as the protons, so they're also 6. So you can look at any combination. So you could be given, if I give you, like here, only given the atomic mass, or I could give you just the number of electrons, and you can work back and figure out the number of protons and the number of neutrons. So any combination of working through the 3 of these, you should be able to do. Okay, so let's go back to this. Okay. One thing I just want to point out, the periodic table that's in your text or that we've been using writes it that way, but sometimes you can see a periodic table that maybe write it a little different. So sometimes you see that Fe has got the 26 up the top, the number underneath the word. In that case, you just the bigger number is always the atomic mass. The smaller number is always the number of protons. And remember, you always have to have whole numbers of protons and neutrons. So even in this case, if you did 55 minus 26, you're going to get something with a 0.8 in it. You have to round that to the nearest whole neutron. You're never going to have fractional numbers of neutrons and electrons. Okay. So you can look at, again, the elemental symbol, and it gives you the number of protons, and you give it the number of neutrons. But some elements have 2 or more isotopes. That means they have different forms that have different numbers of neutrons. So hydrogen, we're used to seeing, has an atomic number 1. It has 1 proton. It's hydrogen. It has one proton that makes it hydrogen. Deuterium has 1 proton and 1 neutron, so the atomic mass is 2, and that's what we call heavy water. If you ever heard anybody talk about heavy water, it's because it has this extra neutron in it. And tritium has 2 extra neutrons, so the mass is 3 because it's 1 proton and 2 neutrons. So sometimes you will see a variety of these isotopes. And there's a table in your text that talks about some of the isotopes of some of the light elements. So we just said that hydrogen had 3 possibilities. Helium also has 2 different possibilities of isotopes. Lithium has lithium-6 and lithium-7. So they still have the same number of protons that makes them lithium, but it has more neutrons. Boron is another example, and even carbon. We just did the carbon-14. Carbon actually has 3 different types of isotopes: carbon-12, carbon-13, and carbon-14. And you can see here the natural abundance. It's mostly carbon-12, with 98% carbon-12, with 1% carbon-13, and a very trace amount of carbon-14. Carbon-14 is what they use for the dating, and we'll talk about that. I don't think we get to that until next semester when we talk about nuclear chemistry. But again, even with hydrogen, the 99% of it is hydrogen with only 1 proton. There's about 0.01% with 1 extra neutron, and there's only a very small trace that has 2 extra neutrons. So this is why some of these numbers are not always whole numbers, because it's an average of these, weighted average of these different numbers. Uranium has a number of different isotopes. So it always has 92 protons, because that makes it uranium. And uranium-235 would be 235 minus 92 would have 143 neutrons. Uranium-238 would have 146, and sometimes there are various other ones. So as you get into the bigger, especially the heavy and transition metals and lactinide and actinide series, some of these have a lot more isotopes. And how you arrive at this average mass is it's the fractional abundance times the weight of that isotope. So for example, the element boron, which we talked about before, 19.9% of it is B10, that has a mass of 10 AMUs, and 80% of it is B11 with a mass of a little more than 11 AMUs. So to find the overall mass, it's the percentage times the weight, you see here, and then a percentage times the weight, and you add it. So it's not an average divided by 2, it's a weighted average, and you get 10.81. And if you look up boron on the periodic table, you'll see that is exactly the value of the atomic mass of boron is 10.81. So we're going to do another example. Oxygen is the most abundant element in the Earth's crust and in the human body. The atomic mass of oxygen has 3 isotopes: oxygen-16, oxygen-17, and oxygen-18. And they're relative weights are 15.99, 16.99, and 17.99 respectively. So calculate the average atomic mass of oxygen using these relative abundances. So we'll go back to our page here, and oops, get back to the page. So oxygen 16 was 0.99757 times the its weight, 15.99.49. Oxygen 17 is 0.038%, which makes it 0.0038 times its atomic weight, which is 16.9991. And then the last one is oxygen 18, which is 0.00205% times its weight, which was 17.9992. And if you put that together, you will get the atomic weight of oxygen. And I just realized that this is 0038, so we gotta put a little O in there because we moved it. It already was O and we made it a percent, so it actually has 3 there. So if you multiply these all together and add it up, you should get the same atomic weight as you see for oxygen on the periodic table. So I'll let you try that. Okay, now let's go back to here. And then the last part was just to do that example. All right. Then we're going to look at ions. When the number of protons and the number of electrons are not equal, the atom is said to be called an ion. So the charge of the atom is equal to the number of protons minus the number of electrons. If the atom gains electrons, it is called an anion and has a negative charge. So for example, when oxygen has 8 electrons, gains 2, it becomes an anion with a -2 charge. An atom that loses an electron is called a cation and has a positive charge. So sodium tends to lose an electron and become a positively charged sodium with 1 less electron. And you can do these in the same way that you would write them, only this time they would write the little charge up in the upper right hand corner. So helium with a 2+ charge would look like that, and magnesium with a 2+ charge would look like that. So we can also look at some examples of this as well. Move this down. So an ion of platinum has a mass number of 195, contains 74 electrons. How many protons and neutrons and electrons does it have, and what is its charge? So the first thing we're going to do is go look up platinum on the periodic table. So let me bring up my periodic table and we'll look up platinum. And we'll see that platinum is, I gotta find it on the periodic table, is atomic number 78. So it's PT, and it's atomic number 78. So that means the number of protons equals 78. It should be a lowercase t. Let me go back to that. So it's always, only the first one is uppercase. So this is lowercase, PT, platinum. So it has 78 protons. The mass number is 195, so that means the number of neutrons is equal to 195 minus 78, and that is the number of neutrons. And I'll let you subtract that. But it says it has 74 electrons, so it should have 78, but it only has 74. So that means what happens is that it lost 4 electrons. So it lost 4 electrons. So it has a positive charge. So this would be written as platinum 4+, like that. Okay? So this is how you would do these for anything that's charged. You do it just the way you normally would, but then take off the electrons at the end.